Hi guys, in this video I want to show you how to debounce one or more push buttons reliably in software. But first of all, why do push buttons bounce? The answer lies in the mechanical property of push buttons. When a push button is pressed, the contact bounces one or more times. This results in a short rebound that lasts a few milliseconds. This results in a sequence of low and high pulses as seen here on these oscilloscope images. In this picture, the button bounces over a period of 1.2 milliseconds and generates 5 falling edges during this time, and each falling edge triggers an interrupt. If we would toggle an LED in an interrupt service routine, the LED would change its state 5 times within 1.2 milliseconds. Therefore, we need to determine a stable state of a button. Basically, there are two different ways to debounce a push button, either in hardware or in software. Since debouncing in hardware requires additional electronic components and space on the PCB, debouncing a push button in software is the better alternative. There are two approaches to debouncing a button. First, check the key state continuously within a loop. Or second, generate an interrupt when the button is pressed and then check the button state within a time window of, say, 20 milliseconds. The first variant is known as polling, but it's not recommended because the microcontroller is constantly busy querying the status of a button. Okay, let's go in detail and find out how we can check a button state after a button press by using an external interrupt and using a timer interrupt where we can check the button state every millisecond. Basically, it is distinguished whether an external edge-triggered interrupt is triggered at falling or rising edge, or also at falling and rising edge. In our example, the external interrupt is triggered on a falling edge. This means that the interrupt pin is biased high via a pour-up resistor as shown in the right schematic. When the button is pressed, the high lever here on pin 4 is poured to ground. This creates a falling edge which triggers an external interrupt. In our case, however, we don't use a pour-up resistor in hardware, but in software, so-called internal pour-up resistors. You can make these settings in your IDE. Okay, so what do we need to do when a button is pressed and triggers an interrupt? Let's take a closer look at this process in this illustration. As soon as the button is pressed, there is at least one falling edge that triggers one or more interrupts. In this example, 3 interrupts would be triggered before the button assumes a stable state after the bounce time. By the way, the same happens when the button is released again. This means that we absolutely have to wait at least 20 milliseconds after the event until we can verify a valid keystroke. Okay guys, let's go through this process in code first. When the button is pressed, the falling edge generates an interrupt. In our interrupt service routine, here HAL GPIO XT callback, which is called at this moment, we also need to know where the interrupt came from. That means which port pin the event occurred on. Fortunately, the interrupt handler immediately gives us the corresponding baud pin over the parameter GPIO underline pin as an integer value. In our SysTick handler, you will find the SysTick handler in the file STM32L4XX_it.c. In your source folder, we check the button after a button is pressed. Of course, you can use another handler or another timer interrupt which will call every millisecond. Here we check every millisecond which button is pressed and the current state of the button, since the SysTick handler was called every millisecond. If the button state is low, a counter increments by 1. Otherwise, the counter is set to 0 if the button state is high. Only when a low signal has been detected 20 times in succession is the keystroke recognized as valid. Here you can see the setup on a breadboard with a Nucleo L412 board and 4 buttons. Let's look at this process directly in the source code. Here we check 2 buttons on GPIO pin 0 and 1. If the button on GPIO pin 0 is pressed, the interrupt handler gives us the value 1 and the first if loop is executed. Here the current state is checked, and if it is 0, button counter is incremented by 1. After 20 low signals, the LED at port B pin 3 is toggled. If a high signal is detected within these 20 milliseconds, the button counter is reset in the else loop. In the last else loop, the button is reset to the value 0. This process can now be used for any button, and this variant is also independent of how long a button bounces. Only when the state of the button is stable for 20 milliseconds, a valid button press is recognized. Okay, that's it. I hope you enjoyed this presentation, and I would greatly appreciate a thumbs up click. Thank you and goodbye.